Hi, my name is Harshavardhan Prasad and my teammates are Harshavardhan and Dishith Chandra. In this video, we are going to discuss about the project that we have worked on during our deep learning course. The project is to detect occurrence of anomalies in Numenta Anomaly Benchmark dataset using unsupervised approach. Let us start from the beginning. What is an unsupervised approach? As the name suggests, unsupervised learning is a machine learning technique in which the models are not supervised using any training dataset. Instead, models itself has to figure out any hidden patterns and also any hidden insights that were presented. It can be compared to learning which takes place in the human brain when we try to learn any new things. Coming to introduction. Largely driven by the rise of Internet of Things and connected real-time data sources, we now have an enormous number of applications with sensors that produce important data that changes over the time. Analyzing these data streams effectively can provide valuable insights for any use case and also for any application. What are anomalies? Anomalies in data identify abnormal behavior with potentially useful information, and they can be different types such as spatial, temporal or contextual. I am going to now explain the differences between spatial and temporal anomalies using an example image. So now consider this particular image. Just consider these points which I have highlighted already. Here the x-axis represents the time frame and the y-axis represents the particular data stream. First consider these 2 points which I am highlighting right now. As you can see, these 2 points are way too different when compared to this whole particular data stream. So these points are called as spatial anomalies. Now consider this particular point. And this point will be treated as an anomaly in this particular small time frame because it is actually way different in this particular time frame. So this point is called as temporal anomalies. We cannot say this point as a spatial anomalies because these temporal anomalies are present everywhere in this particular data frame. So this is the difference between spatial anomalies and temporal anomalies. Coming back to the presentation. The detection of anomalies in real-time streaming data has practical and significant applications across many industries. Use cases such as preventive maintenance, fraud prevention, fault detection, and monitoring can be found throughout numerous industries such as finance, IT, security, medical, energy, e-commerce, agriculture, and even in social media. Temporal anomalies are often subtle and hard to detect in real data streams. Detecting these temporal anomalies in practical applications is valuable as they can serve as an early warning for the problems within the underlying system. Now coming to the data streaming applications, which will be involving analyzing a continuous sequence of data occurring in real time. So in this data system, this system observes each data record in sequential order as they arrive, and any processing or learning must be done in the online fashion. Let the vector xt represents the state of the real-time system in this particular data stream. So let us write this model using the text form and so let's xt represents the state of the data stream, and right now as the data is received in every particular time frame, we can consider the data stream as xt minus 1 xt and then xt plus 1 and then so on. So in this particular data stream right now, consider the example of this particular data stream as a data center. So components of this particular xt might include CPU usage for various servers, bandwidth measurements, latency of server requests, and so on, etc. At each point of time t, we would like to determine whether the behavior of the system is unusual or not before the xt plus 1 arrives. So the system must be able to consider the current and the previous states to decide whether the system that we got is anomalous or not immediately. So practical applications impose additional constraints on the problem such as human intervention errors. For example, the sensor streams are large in number and at high velocity, this will leave very little opportunity for humans, let alone experts, for causing of interventions. In many scenarios, the statistics of the system can change over time. A problem known as concept drift, which is actually considered the example of a production data center, and whenever there is a software upgrade, and then this results in the configuration changes which will be occurring at any time, and it may alter the behavior of this particular system. In such cases, models must adapt to the new definition of the new normal in an unsupervised automated fashion. So given the above requirements, we define the ideal characteristics of the real-world anomaly detection algorithm as these following rules. So as I mentioned above, Predictions must be made online, that is, the algorithm must identify state xt as normal or anomalous before receiving the subsequent xt plus 1. The algorithm must learn continuously without a requirement to store the entire stream, and the algorithm must run in an unsupervised automated fashion, that is, without data labels or manual parametric tweeting in order to reduce any errors. Algorithms must adapt to dynamic environments and concept drift, as the underlying statistics of the data stream is often non-stationary. Algorithms should make anomaly detections as early as possible, and algorithms should be able to minimize false positives and also false negatives. Coming to the frameworks to detect anomalies, we used a particular framework called as HTM. HTM is a hierarchical temporal memory. So based on known properties of cortical neurons, HTM is a theoretical framework for sequence learning in the cortex. HTM implementations operate in real time and have been shown to work well for prediction tasks. HTM networks continuously learn and model the spatio-temporal characteristics of their inputs, but they do not directly model anomalies and do not output a usable anomaly score. So this is the picture which depicts the overview of anomaly detection using an HTM. Now my partner Dishith Chandra will be continuing.
Hi, I am Dishith. Let's see the overview of our process, anomaly detection using HTM. At each point in time, the input data xt is fed to a standard HTM network. We perform two additional computations on the output of the HTM. We first compute a measure of prediction error st. Then using a probabilistic model of st, we compute lt. It is a likelihood that the system is in an anomalous state. Now let's discuss the breakdown of the core algorithm components within an HTM system. In this figure shows the core algorithm components and represents within a typical HTM system. The current input xt is fed to a encoder and then a sparse spatial pooling process. The resulting vector a of xt is a sparse binary vector representing the current input. Here you can see a of xt it is. And then the sequence memory, it is the heart of the system. This component models temporal patterns in a of xt and outputs a prediction in the form of another sparse vector pi of xt. Here you can see pi of xt is a prediction of a of xt plus 1. HTM sequence memory consists of a layer of HTM neurons organized into a set of columns. The network accepts a stream of inputs encoded as sparse vectors. Here you can see in this figure, HTM sequence memory models one layer of cortex. The layer consists of a set of mini columns with each mini column containing multiple neurons. Here in the left, an HTM neuron models the dendritic structure of pyramidal neurons in cortex. Here you can see in the right side. An HTM neural models dendrites as an array of coincidental detectors, each with a set of synapses. The network accepts a stream of inputs encoded as sparse vectors. It models high-order sequences. Those are sequences with long-term dependencies using a composition of two separate sparse representations. The current input xt and the previous sequence context xt-3, xt-2, etc. are simultaneously encoded using a dynamically updated sparse distributed representation. The network uses these representations to make predictions about the future in the form of a sparse vector. Representing high-order Markov sequences with the shared subsequences ABCD versus XBCY. Here, each sequence element invokes a sparse set of cells within mini columns. Cells that are predicted through lateral connections prevent other cells in the same column from firing through intra-column inhibition, resulting in a highly sparse representation. As shown in the figure, such representation can maintain past context because different cells respond to C in two sequences. Here you can see C dash and C double dash. They can invoke the correct prediction of either D or Y depending on the input from two time steps ago. Here you can see in this figure the black one are the active cells and the red ones are the predictive cells and the grey one are the inactive cells. Here this image shows how the sparse representations are used to represent temporal patterns and disambiguate sequences with long-term dependencies. Planning happens at every time step But since the representations are highly sparse, only tiny percentage of synapses are updated. Now let's discuss about the how we compute the prediction error. Given the current input xt, a of xt is a sparse encoding of the current input. This is we discussed earlier, and pi of xt minus is the sparse vector representing the HTM network's internal prediction of a of xt. The dimensionality of both vectors is equal to number of columns of HTM network. We use a standard value of 2048 for the number of columns in all our experiments. Now let's say ST be the prediction error. It is a scalar value inversely proportional to the number of bits common between the actual and the predicted binary vectors. This is the mathematical representation of predicted error ST. It is like ST equal to 1 minus dot product of pi of xt minus 1 and a of xt divided by mod of a of xt. Here mod of a of xt is the scalar norm, that is the total number of 1 bits in a of xt. In the equation error, st will be 0 if the current a of xt perfectly matches the prediction, and it is 1 if the two binary vectors are orthogonal, that is they share no common 1 bits. St thus gives us an instantaneous measure of how well the underlying HTM model predicts the correct input xt. Changes to the underlying statistics are handled automatically due to the continuous learning nature of HTMs. If there is a shift in the behavior of the system, the prediction error will be high at the point of the shift, but will automatically decay to 0 as the model adapts to the new normal. An interesting aspect of this metric is the branching sequences are handled correctly. In HTMs, multiple predictions are represented in pi of xt as a binary union of each individual prediction. A moderate number of predictions can be represented simultaneously with exponentially small chances of error. The above error handles branching sequences gracefully in the following sense. If two completely different inputs are both possible and predicted, receiving either input will lead to a 0 error. Any other input will generate a positive error. Now my teammate Harsha will take care of other stuff.
Hello, my name is Harshavardhan, and in this video I will be discussing about computation of anomaly likelihood. Coming to the computation of anomaly likelihood, the prediction error described above represents an instantaneous measure of the predictability of the current inputs. It works well for certain scenarios, but however, the underlying system is inherently very noisy and unpredictable, and instantaneous predictions are often incorrect. To handle this class of scenarios, we introduce a second step. Rather than thresholding the prediction error directly, we model the distribution of error values as an indirect metric and use this distribution to check for the likelihood that the current state is anomalous or not. The anomaly likelihood is thus a probabilistic metric defining how anomalous the current state is based on the prediction history of the HTM model. Now coming to the computation, to compute the anomaly likelihood, we maintain a window of the last W error values. We model the distribution as a rolling normal distribution where we take the sample mean and variance, and we continuously update from the previous values using the given formulas. And the duration for this calculation of mean and variance, we take W1, that is certain duration which depends on particular dataset which we are using, and we compute a recent short-term average of the prediction errors and apply a threshold to the Gaussian tail probability to decide whether or not to declare an anomaly. We define the anomaly likelihood as the complement of the tail probability, that is as follows. Coming to the experimental results. In these experimental results, we summarize the NAB scores for each algorithm across all application profiles, including the 3 NAB competition winners. In addition to these algorithms described above, we also use 3 particular control detectors in NAB. First one, the null detector, which runs through the dataset passively, making no detections and accumulating all false negatives, and a perfect detector, which is an oracle that outputs detections that would maximize the NAB scores. That is, it outputs only true positives at the beginning of each window. The raw scores from these two detectors are used as scale to score all the other algorithms, which are between 0 to 100. And we also included a random detector that outputs a random anomaly probability for each data instance, which is then threshold across all data sets for a range of random seeds. And the score from this detector offers some intuition for chance level performance on NAB. And overall, we see that the HTM detector using the anomaly likelihood gets the best score. The HTM detector using only prediction error performs moderately well compared to the other state of art models, but uh, using the anomaly likelihood step significantly increases the scores, which is as follows shown here. And coming to the conclusion, in the conclusion, we can say that with increase in controlled connected real-time sensors, the detection in anomalies in streaming data is becoming increasingly important, and the use cases cut across a large number of industries. We believe anomaly detection represents one of the most significant near-term applications for machine learning in IoT. In this presentation, we discussed a set of requirements for unsupervised real-time anomaly detection on streaming data and discussed about HTM framework. Based on the HTM framework, which is an unsupervised technique, the algorithm is capable of detecting spatial and temporal anomalies in the predictable and noisy domains. The algorithm meets the requirement of real-time, continuous and online detection data without look-ahead and supervision.